Hey everybody, Dr. Berkey here. In this video, I'm going to address the concerns of a lot of people out there because you're kind of sick of hearing this idea that if you only have a sample of data, when you calculate an estimate of the population variance, you have to divide by n-1, whereas if you have all the data and you calculate the population variance, you use n. And everybody asks, why do we divide by n-1? And I teach this class, and I have students ask me, and I remember some of the answers that professors gave me in the past when I asked the same question. And quite often you'll just hear, shut up, it's n-1, just memorize it. The answer I give my students quite often is, well, it's complicated. There's a proof, but you don't want to go through the proof because it's not very satisfying. You sort of understand where this n-1 comes from, but it doesn't really help you get it. What is it about the n-1 that is fixing things? That's what this video is for. I'm not going to go through a proof. If you want a proof, you can just Google it. I'll show you somewhere you can get a proof, just in case you're not aware of where you can get a proof. Just Google proof of Bessel's correction. This is a website, gregoryunderson.com. And it goes through the standard summation notation, doing expected values, etc., etc., etc. And then when you get down to the end, you get this n-1. Fine, just not very satisfying. So how can we go through this and try to give you a gut feeling about why n-1 actually works and actually kind of why it makes sense? I'm going to attempt to come at that a few different ways here in this video. So here's what I want you to understand. First question, why divide by n-1? If we don't divide by n-1, our estimates of the variance. So we have a sample of data. We're really trying to learn the best estimate we can of what is the population variance. If we don't divide by n-1 and we divide by n, our estimates will be biased. They'll be too small. So that's the first thing just to understand as we get going here. Question 2, why? I want to know why. Just don't tell me that the fact that this is true, but why is it true? Okay, we'll try to get at that a little bit. And I also want to make sure you understand at the beginning here, and we'll come up with some evidence for this, but it isn't really because we have a sample of data. The fact that it's a sample of data isn't why we need to divide by n-1 instead of n. It's really because we have a sample mean. So if somehow we wanted to estimate the population variance, we didn't know the population variance, but we did know the population mean, then we would not have this problem. It all comes from the fact that we only have the sample mean. It's not really just because we have a sample of data. So if there was some world where there was a machine making a product and we knew the population average, we knew the machine was set to produce products that had an average weight of a pound, something like that. And what we needed to know, though, was what's the population variance? We needed to estimate the population variance. We can take a sample of items off that production line. If we know the population mean it's a pound, we could calculate the sample variance dividing by n instead of n-1, and our estimate would no longer have that bias. Let's just spend 10 seconds here getting familiar with these formulas. So what we're doing in the numerator of these formulas is we're taking each number and subtracting the mean. Here it's the population mean. When we're using Bessel's correction, it's the sample mean. And we're getting those deviations. So these numbers here, where we take numbers and we subtract the average, those are what we call deviations. And what we do in both formulas is we square those deviations and we sum them up. So what we have is the sum of squared deviations. And here's the lesson we're going to learn. Because we're plugging in the sample mean here, our sum of squared deviations here is going to be smaller than it would be than if we plugged in the population mean. So it's the sum of squared deviations in the numerator that are going to be too small, and it just so happens that they are going to be too small by the difference of dividing by n and n-1. And we're going to see that with some simulations in just a moment. So I want to help you understand why it is that when we have the sample mean and we plug that into a formula where we're calculating the sum of squared deviations, I want to help you understand some justification for why that sum of squared deviations might be too low. And so this is not a proof of the n-1 and where it comes from, but this is just one thing that's good to understand, is that when you plug in the sample mean there, it's going to minimize that sum of squared deviations. Now, to tell the truth, when you plug the population mean in here, when you have all the population data, that also minimizes the sum of squared deviations. But the problem comes from having the sample mean. We're using the wrong number. We're using the wrong number. We're using the sample mean is going to minimize this sum of squared deviations, but we're kind of calculating the wrong deviations over here. What we really want to know is how far each of those points are from the population mean. Instead, we're calculating how far they are from the sample mean. So let's just spend a minute looking at that idea. So suppose we just were wondering, for mathematical curiosity's sake, what number a could I plug into this formula where I take each number, I subtract a from it, I square them and add them up, and I get a sum of squared deviations. What number a would minimize those? There are some fancier proofs and derivations, but I'm trying to give you a gut level feeling and understanding here. I'm not trying to baffle you with my proving skills. I'm trying to show you some numerical things that help you understand what's going on here. So if we take this squared term here and we use the FOIL method, the first, outer, inner, and the last terms, and we multiply the first times the first times the last, and we add up those terms, then what we get is the sum of xi squared. That's the first. And then when we do the outer and the inner, we're going to end up with minus 2a times the sum of the numbers, the sum of the xi's. And then the last term is the sum of these squared. Now, to simplify that just a little bit, when we go from here to here, all we're saying is that if I add up a number, a certain number of times, then I'm going to get n times that number. So a squared plus a squared plus a squared plus a squared. If I add that up n times, I get n times a squared. So what we have here is the formula for a parabola. And here's just a graph of a parabola. And what we know about a parabola is there's a minimum, right? So all we're saying is, here's a function. It turns out to be a quadratic equation. We know that's the graph of a parabola. And parabolas, this kind of parabola is going to have a minimum, okay? It's going to be a convex shape like this. Now, let's just play with a small data set just to get a feel for what's going on here. Suppose here's our data. Our data is 11, 11, 6, and 4. So just a very small data set with 4 numbers in it. And the average of those 4 numbers is 8. And we have n equals 4. That's 4 numbers, okay? Now, if we want to see what is this equation going to look like if we calculate all these numbers for this data, then if we get the sum of x squareds, that's the first term here, then we have 11 squared plus 36 plus 16. Well, that's 294. We also need the sum of the x's here. If we add those numbers up, 11 plus 6 plus 4, we get 32. And then we plug those numbers into this equation, we get 294, the sum of the x squareds, minus 2 times this number a. We're just going to pick a number a to minimize the sum of squared deviations in a minute. So minus 2a times 32, the sum of the x's, plus n times a squared. Well, n is, we have 4 numbers, so 4a squared. And so when we just rewrite that, the normal way that we write a quadratic equation, 4a squared minus 64a plus 294. Now, if we minimize, there's 2 ways to think about minimizing an equation like this. I like calculus, so what I would do is I would take the derivative of this function with respect to a. A derivative tells you the slope, and we're looking for the place on this parabola where the slope is equal to 0. And the slope is equal to 0 down there on the bottom. So what we're trying to ask is, what value for a down here is going to find the minimum, the bottom of that parabola, the minimum of the sum of squared deviations. So if we take the derivative of that, the derivative of a polynomial, you just multiply by the exponent and then subtract 1 from the exponent. We end up here, 2 times 4 is 8a, subtract 1, you end up with 8a to the first. And then the derivative of minus 64a is just minus 64. We can set that equal to 0. We solve, we get a equals 8. Now for those of you who aren't calculus fans, fine, that's why I have the graph of this parabola. All we have to do is plot the parabola and zoom in, and we can see that the value of a that minimizes that parabola is right there at 8. Okay, so we can just either look at a graph and find that minimum, or we could do some calculus and find the minimum. Now, what's so special about the number 8? Oh yeah, 8 is the average of those numbers. So if we have a sample of data and we plug in the sample average, that's going to give us the minimum, the lowest possible sum of squared deviations value possible. And if you pair that together with the idea that we're not really interested in getting the sum of the squared deviations between each number and the sample mean, x bar, what we really want to know when we're calculating an estimate of the variance is what's the sum of the squared deviations from the population mean. The fact that we're using the data, the sample of data, to calculate the number that minimizes this, that makes it as small as humanly possible, is part of the reason why when we use x bar in this equation, the sum of squared deviations is too low. If we were to use the population mean, it would not be biased like that. Okay, now that first reason, it seems a little weak. Dr. Berkey, you're supposed to be giving us a gut feeling, a real understanding for why that n-1 makes a difference. What you just did there just seemed like more mathematical distraction. I agree. Let's go on. Let's play with some numbers in R. Now, if you're not familiar with R is a free statistical programming package. You can download and install it on a Mac or a PC or on a Linux machine. You can download the code. Also, make sure you download this handout. You can download the code. Here's a link in the handout so that you can download this code, or if you want to type it, that is fine as well. But it's much easier just to download it, copy and paste it into R. Let me just give you a brief preview, then we'll jump into R. Here's what we're going to do. I'm going to show you that if you use the wrong formula with samples, the wrong formula dividing by n, we don't use that Bessel's correction, then what we're going to see is most of those estimates of the population variance are going to be too low. They're going to be biased. They're going to be biased in a downward or a too low direction, all right? Well, we're also going to see that if we divide by n, the average of many sample estimates of the population variance are going to be too low. So we're going to see most individual estimates will be too low. We're also going to see that the average of many, many estimates will be too low. They're going to be biased. Item number 3, the amount of bias just happens to be the difference between dividing between n and dividing by n-1. So we're going to be able to see how biased our answers are when we divide by n. And we're going to see that dividing by n-1 fixes that problem. Number 4, we're going to see that even if we just have samples of data, if instead of plugging in the sample mean into that variance formula, if we plugged in the population mean there instead, so if we instead know the population mean and we plug it in this formula, then we don't have to divide by n-1, and our estimates are going to get much, much closer to being correct. So if we use the population mean in that formula, we don't have to divide by n-1. And number 5, the last step, we're actually going to use Bessel's correction. We're going to calculate the estimates of the variance the correct way, and we're going to see, oh yeah, those are closer to what they should be. Okay, let's dive into R and get going. So I'm here using Rstudio Cloud, and if you go to rstudio.cloud on the internet, you can set up a free account and you can play around with R without having to install it on a computer. You can get a free account. You have limited numbers of hours that you're allowed to use this free account per month, but you'll have plenty of free time to follow along if you want to use rstudio.cloud. Okay, here's what we're going to do. We're going to come up with some made-up data. You could use real data and you'll get exactly the same kind of results that we're getting here. But just to make this simple for everybody to follow along, our play data is going to just be a list of the numbers from 1 to 2000. Okay, so I'm going to call that data var.data, the numbers from 1 to 2000, Control Enter. And when we hit Control Enter, so you have to hold down Control, then hit Enter. Here's our values, our variance data, 1 to 2000, 1, 2, 3, 4, etc. Now, R does not have a population variance formula. It has a function called VAR, but VAR is a sample variance formula. It's going to be very rare in a statistical program that you'd want to calculate a population variance. So here I have written a population variance formula here. It's a function of X. We need to know how many observations are in the sample. We need to know the sample mean. And then here we are just dividing by n, and we have the sum of the squared deviations right there. Okay, so we just go anywhere in this formula and we hit Control Enter. Well, let me try the first line instead of the middle. Okay, I just went up to the first line there and hit Control Enter. And now we have a function, population variance. Now let's use that function to calculate the true variance of our data. So our data is called var.data. We have a function to calculate the population variance. Let's calculate it and see what it is. And then if we just type that name popvar, the real variance of those numbers, 1 through 2000, is 333,333.2. What does that mean? Nothing much, really, but if we take the square root of that, we get the standard deviation. Standard deviation, about 577. That just tells us that it's common, that's a common deviation, a common distance from the average, that numbers in our data set are from the average, is about 577. In other words, most of the data is going to be within the mean, which is going to be around 1,000, actually slightly bigger. So the average of the numbers 1 to 2,000 is 1,000.5. It's going to be common for the numbers in our data to be about 577 higher or lower than average. That's going to capture most of our data. That's not a technical definition of standard deviation, but it's a good way to think of it. All right, now what we're going to do, we have our data. Our population of data is the numbers 1 through 2000. Here we're going to take a sample, not just one sample. We're going to take 1,000 samples. So here we're taking 1,000 samples. We're actually taking 10,000 samples. And then I'm splitting them up into 1,000 different groups of 10 observations. So we're taking 1,000 samples of size 10 from our data here. And this replace equals true means we're going to draw a number from 1 to 2,000 and put it back. Draw a number from 1 to 2,000 and put it back. We have to put it back because we're drawing 10,000 from a group of 2,000. That choice is not mathematically important for the results that we're going to see. So let's hit Control Enter there, and now we have our samples, and let's just click on that so you can get a feeling for what we're talking about here. So here we have 1,000 rows of 10 observations. So here's our first sample size of 10, 854, 340, 356, etc. And we can scroll all the way down to our 1,000th sample of 10 observations. What we're going to do is we're going to calculate the variance of each row of each sample. All right. So let's calculate our sample variance estimates, but we're going to divide by n instead of dividing by n-1. And we're going to see what goes wrong when we do that. They're going to be too small. So wrong.vars is apply to my samples the population variance formula. 1 says do it for each row. So we're going to end up with 1,000 estimates of the population variance. Let's just look at the first 10 estimates that we got. Now keep in mind that the truth was around 333,333. So this one's too low, this one's too high, too low, too high, too low, too high, too low, too low, too low, too low. Now if those first 10 are any indication, most of these are too low. Now let's count up. How many of these estimates of the population variance are too low? The easiest way to do that in R is just to get it to check. Which of these wrong variances in this list of 1,000 variances here, which of them are less than the true value of 333,333 that we calculated? And then when it does this check, it counts them as either ones if it's yes or zeros if it's false, and we add those up. So this says that 626 of those estimates are too small. That means that the other 374 are too large. Now don't panic if your results are a little different from mine. Because we are taking random samples here, your results are going to be a little different from mine, but they're going to be pretty close. What you're going to find is that the majority of those estimates are too low. It's probably going to be around 60 to 65% of your estimates are too low, kind of similar to what I found here. And only 374, so 37.4%, are too big. What we would expect if our estimator was unbiased, our formula for calculating estimates of the population variance. If it was unbiased, we would expect about half the time we would be overestimating the population variance, and about half the time we would be underestimating. This is a big difference from half and half. So just a reminder, why? Well, it's because we're dividing by 10 in the formula instead of 9. So let's look at a graph and see what's going on. Here I'm just telling it not to show scientific notation so often. And if we look at a histogram, it's not going to show the histogram unless I make this little plot window a little bigger. All right, let's run that line 27 again. Let's make this a little bit bigger. So this is just so you can see that, remember, our true value for the population variance is around here, 333,000. And you can see that by far most of these values are lower than that. We can see that bias in our estimates. So just to remind ourselves again what that true value is, 333,333.2. Now let's make another histogram, but let's make the bars, let's divide it into a little bit more bars just to get a little bit better look here. Yeah, now we can clearly see that all those values over here are lower than the truth. Only these ones over here are higher. Now what we're also seeing here, this is not going to be a symmetric bell-shaped distribution. The kind of distribution we're looking at here with estimates of a population variance is an example of a chi-squared distribution. It can't be below 0, so it's kind of truncated over here at 0, and it's going to be skewed to the right. So on average, what percentage are our estimates wrong? What we want to know. So here I'm taking the average of all those 1,000 estimates of the population variance to see what it is. Just slightly above 300,000. Just slightly. So let's look at the ratio of that number to the truth, 333,333, as a percentage. So our estimates of the population variance on average are only about 91% of the right answer, And then if we flip that, we see that they're about 10% too big. Now, most of the time when I do this, and what you'll probably see when you do this, is that this number is a little closer to 90%, and this number is a little closer to 111%. On average, when we do this experiment, and we have a sample size of 10, and we're dividing by 10 when we should be dividing by 9, our answers are going to be about 10% off if we look at it this way. They're going to be about 11% off if we flip that ratio and we look at how much bigger the truth is compared to our estimates. And it turns out that's the difference that you get when you should be dividing by 9 and you divide by 10 instead. A 10 or 11% difference depending on how you look at it. All right, item number 4. What if we had that machine we were talking about and we knew the true population mean somehow? We don't know the variance, but we did know the mean. What would happen if we plugged in the population mean into the formula? Would that fix the problem if we still divided by 10? Well, let's calculate the mean of our population of data, 1000.5. Now I'm writing a variance function, assuming we know that mean is 1000.5. So I'm putting the population mean in there instead of the sample mean. So let's define this function, Control Enter. So now we have our population variance function 2. And if we click on it, it shows us it's putting in that known population mean. This is not a realistic situation, as I said before. But let's go back and let's calculate an estimate of the population variance for each of our 1,000 samples in our data, plugging in that population mean, assuming that we knew it somehow. So here we have better.variances.1. I'm going to apply that new formula where we assume we know the population mean. Control Enter. Let's just look at the first 10 items there. Okay, too low, too high, too low, too high, too low, too high, too low, too low, too low, too low. Okay, well, maybe it's not any better if we just look at those first 10. But this is why we do 1,000 estimates. Let's look at the average of the 1,000 estimates and see if they're closer to 333,333. And it sure is. It's actually a little bit too large now. Now just for fun, let's look at a histogram here. Histogram bettervars.1 breaks equals 30 to give it around 30 bars in our histogram. Okay, I got to make that window a little bit bigger and then try again. There we go. And now here's the truth, right? Around 333,333. And now we can see that about half of them are larger and about half of them are smaller. So things are improving a lot. Just now we know the population mean. So I hope this has given you a better understanding of where this bias comes from when we have a sample. Okay, now lastly, let's calculate the variances the right way, the way we would, assuming we don't know the population mean, but we use Bessel's correction and we're going to divide by n-1. We're going to divide by 9. So here we're using the var function that is in R that will divide by 9 since we have sample sizes of 10. And we'll call all these 1,000 estimated variances. I'll put them in a list called bessel.var.ests. Control Enter. So how many of them are too large now? Only 493 are too large. So that means that 507 are too small. We're getting very close to that 50-50. Now again, this is random. These are random samples. We're never, well, I won't say never. We're not going to get 50% exactly too high, 50% too low every single time, but we should get something pretty close to 500 on each side. Let's look at a histogram here and see what does this look like when we divide by 9. Again, very similar looking histogram here where we have about half less and about half larger. And let's look at the average of all those estimates. Again, a little bit too big. So just to do a quick review here. Why is it that we divide by n-1 when we have a sample? It's mostly because we only know the sample mean. If we knew the population mean and we calculated using sample data because we didn't know the variance, but we knew the population mean, we could divide by n and our estimates would be very good. If you only know the sample mean, dividing by n-1 is the best estimate, the best, most accurate estimate that we can have for trying to get a feeling for what is the size of the true population variance. So what we saw, if we divide by 10, if we divide by n instead of n-1, by far most of our estimates are going to be way too low. We also saw the average of all those 1,000 estimates was way too low. Because we divided by 10 instead of 9, it was about 10% too low. And that amount of bias from dividing by 10 instead of 9 should be about 10%. So that gives you some confidence that that n-1 really is the right fix to use. And we saw that again, that if we plugged in that population mean, our estimates no longer seemed to be biased. It seemed to be about half of them were larger than the truth, about half of them were smaller than the truth. And we saw that using Bessel's correction did give us what seemed to be unbiased estimates as well. So the lesson here, we divide by n-1 because that gives us unbiased estimates. Of course, there are proofs that will demonstrate this, but the proofs aren't very satisfying for most people. I want to know, how does it work and is it doing the right thing? I never like just trusting that the answer is correct. And hopefully by following along here, now you have a little bit more confidence and a little bit more understanding about why Bessel's correction is a thing. As always, if you have any questions, please let me know in the comments down below. But otherwise, I wish you the best of luck in all your studies. Bye-bye.